So we continue to look at a more involved example of discharging. And to do this, let us look at some ideas behind the discharging method. So one notion that I want to look at is that idea of reducibility. So let phi be a class of graphs closed under taking subgraphs. Okay? So we want to look at graphs which are hereditary, right? Hereditary means that if you take subgraphs, the property still remain. For example, planar graphs are having this property, right? Because any subgraph of a planar graph is also planar. But not all graphs have this property. For example, if I just say non-planar, right? If I take subgraph, it could be planar. So that does not belong to the class. So that kind of classes I cannot take. So I take a class of graphs which are closed under taking subgraphs. So pi be such a class. Then I have some graph property that I want to establish. Let's say property P. It could be anything like what we just wrote before, or some other property like colorability, or chromatic number, right? Or anything else, right? Like some existence of some small neighbor, right? Or existence of a neighborhood where some property is true. I mean anything like this. So let P be some graph property. And our aim is to prove that graphs in pi, right, in the class that we are looking at, all satisfy the property P, right? Every graph in this class has this particular property. Now, this is what we want to prove. Okay. Now, if we are looking at such a question, then we say a set of configurations, right? Configuration is basically a substructure or property. Set of configurations is said to be reducible for a property P if no minimum counterexample to the property can contain any of these configurations. Okay. So I say that a set of configurations is reducible for a given property if no minimum counterexample to P can contain any of these configurations. So what is the meaning of this statement? Let us look at a graph and a given property, right? Now, if the graph does not satisfy this property, then we say this graph is a counterexample to the property. Okay? Now, if I am looking at a class of graphs, what I can do instead is to a set of configurations is said to be reducible for a property P if no minimum counterexample to P can contain any of these configurations. Right? Now we say that a graph is a counterexample if this graph does not satisfy the property that we are looking at. Now, if you are looking at a class of graph, okay, so a class of graphs, we say has a counterexample, then we can look at all possible counterexamples. Okay? So if you can find at least one graph which is a counterexample to the property, which does not satisfy property, then we look at we can talk about all possible such graphs which does not satisfy this, right? So look at all possible counterexamples. Then we can define some kind of minimality, right? We can say that the graph with the smallest number of vertices and edges, right, which does not satisfy this property. Because there are at least some graphs which violates the property, we can talk about the one with the smallest size. So this kind of graphs we call minimum counterexamples. Okay? So what we are saying is that a substructure or a configuration is reducible if minimum counterexamples cannot contain these configurations. So what it actually means is that if you have a graph And if this graph has this substructure, this reducible configuration, right? And if the property is not true for this graph, then even after removing this particular substructure, the remaining graph will also be a counterexample. Okay, that the counterexample cannot be a minimum one, right? You can still find a smaller counterexample. So such cases are called minimum counterexample. Such configurations are called reducible configurations. Now, suppose we can show that you can find a set of reducible configurations that cannot be avoided in the class pi. Okay, so I say that I have a reducible configuration and I know a set of reducible configurations, and this is unavoidable in the class pi, which means that every graph in the class pi must have at least one of these configurations, right? Without having one of these, no graph in this class can be there. So if I can show this, then what does it say? It says that every graph in this class pi contains one of these configurations. Now, if any graph in this is a counterexample to the property, then this cannot be a minimum counterexample, right? Because if there is a minimum counterexample, we are saying that then it cannot contain the reducible configuration. So we are saying that none of the graphs in this class can be a minimum counterexample. But if there is a counterexample, there is a minimum counterexample, because you look at all possible counterexamples, find the one with the minimum size. So therefore, if you show that a reducible configuration is unavoidable, then we have the proof that the property must be true for the class. So the idea of discharging is to show a set of reducible configurations is unavoidable, right? In that part and that part alone, we will use the discharging method. So the idea is to show some structural properties like reducibility, reducible configuration. Now the reducibility of this configuration that you have to do separately. So once you show a configuration is reducible, you can try to use discharging method to show that it is unavoidable in the class. And that is the way this method is usually used. So now let us look at a more concrete example. Right, so here was the crux of the idea. Discharging method helps to establish the unavoidability of reducible configurations in a class pi. If there are no minimum counterexamples for a property P in pi, there are no counterexamples for this property in pi. And therefore, the graphs in pi satisfy the property P. Now we are going to look at a very interesting result. This comes from the the questions that we were looking at before, like four color theorem, right? So we mentioned four color theorem. So what was four color theorem? The four color theorem says that every planar graph can be vertex colored such that no adjacent vertices get different, distinct, no adjacent vertices get the same color, using at most four colors, right? Every planar graph admits a four coloring. So you can color with less than or equal to four colors. But now the question is that if all planar graphs are four colors, does every such graph require four? Obviously no, right? It says that at most four. Now the question is that, okay, which graphs actually require four? Which graphs will do with three? Which graphs will do with two? Right, etc. Now the case, two is very easy, right? We know that the graph is two colorable if and only if it is bipartite. So therefore, even for planar graphs, it is two colorable if and only if it is bipartite. So bipartite planar graphs are easy to characterize. So therefore, that question is resolved. Now the question is that, okay, when can you say the graph requires four colors or three colors, right? So can you say that, okay, this class of graphs require only three colors, or this graph requires 4 colors. So there were several attempts to resolve these kind of questions. Many of them are still unresolved. And one of the interesting questions was an old conjecture. Okay? So this conjecture was that suppose you have planar graphs, right? Now, if you take a planar graph and you say that you don't allow any triangles in it, okay? If there is no triangle, then you know that the triangle-free planar graph has at most 2n minus 4 edges that we proved, and this will easily show us that, like, the graph can be 3-colored. Okay? So planar graphs without triangles can be 3-colored, which is very easy to show. I want you to come up with a proof. If you want a nice exercise, you can think about this. And so therefore that is not interesting for triangle-free planar graphs. So we will allow planar graphs with triangles. Now the question is that, okay, suppose we have planar graph, but we don't allow 4 cycles or 5 cycles. Okay? Now it turns out that planar graphs without no 4 cycles only, right? If you just forbid 4 cycles, then you can find examples where you need 4 colors. So therefore, then somebody asked, okay, what if I don't allow 4 cycles and 5 cycles? So the conjecture said that if you have planar graph where there is no 4 cycle or 5 cycle, then the graph is 3-colorable. Now this conjecture was open for many years. Only very recently, like in 2 years before or 3 years before, it was maybe, I don't know, maybe 4 or 5 years before, it was disproved. But it still gives many other interesting questions. So what we are going to show is that something related to this conjecture. Okay? So we are going to prove the following theorem, that every planar graph that does not have cycles of length 4, 5, 6, 7, etc. up to 11. Okay, there is no 4 cycle, 5 cycle, 6 cycle, 7 cycle, etc. No 10 cycle, no 11 cycle. Okay, so if all the cycles are not there, then the graph is 3-colorable. So we have just made it weaker by adding more forbidden cycle, right? And we are going to prove it using discharging method. Now, let me mention a little bit about this. So, one person proved this very easily, right? Where if you don't allow 4 to 11 cycles, then we can say it is 3-colorable. Then, after some trials, we could see that, okay, this is easily improvable to 4 to 10. So somebody proved that, okay, if there are no cycles of length 4 to 10, then the graph is 3-colorable. Now this second part, right, 4 to 10 can be a good homework question after you do this lecture. Then somebody improved it further, saying that, okay, if there are no cycles of length 4 to 9, then the graph is 3-colorable, planar graph. Again, after some time, somebody improved it. If there are no cycles of length 4 to 8, it is also 3-colorable. And finally, with much more difficulty, somebody proved that if there are no cycles of length 4 to 7, then the graph is 3-colorable. Then after this, somebody proved that the conjecture, original conjecture, that if there are no 4 to 5 cycles, then the graph is 3-colorable is false, right? You need 4 colors. They come up with counterexample saying that, okay, these graphs have no 4 cycles or 5 cycles, which are planar, but still requires 4 colors. So now the only question that remains open is that if there are no 4 cycle, 5 cycle, or 6 cycle, then can you say the graph is 3-colorable? I mean, I don't mean the only question, like, one natural question, which is still open. Okay, so this is, so if you study this method and read up some more interesting follow-up papers, you may be able to look at this technique again. All these proofs are by discharging method, by again, and then try to prove that if there are no cycles of length 4, 5, or 6, then the graph is 3-colorable. If you can do that, it's a very, very nice result. and we'll be very happy to see it. Okay, so without further ado, let us try to prove this very weak result, right? One of the weakest in this chain. Right? That if there are no cycles of length 4 to 11, the graph is breakable. So we start with a set of reducible configurations. So I claim that for the three colorability of graphs, a cut vertex and a vertex of degree less than or equal to is a reducible configuration. Is a set of reducible configurations. Okay, which means that if you are talking about three colorability of graphs, minimum counterexample to three colorability cannot contain cut vertices, right? And minimum counterexample to three colorability cannot contain vertices of degree less than or equal to. Again, these are two easy, very easy to prove, statements. So I want you to think about this and try to prove it yourself before going into the next phase. So stop and then wait for some time. Try to work out this yourself. Show why cut vertex and vertex of degree less than or equal to cannot be part of minimum counterexample to three colorability. Okay, let us look at why. So let us take a cut vertex. Okay. So suppose G is a minimum counterexample to three colorability, and the graph G has a cut vertex in it. Okay, let X be a cut vertex in this graph. So we have this cut vertex. So what is by definition of cut vertex, right? If I remove it, I will get several components. So let us say that C1 to Ck are our components, right? After removing X. C1, C2, C3, etc. up to Ck. So these are the components. C1 to Ck are the components of this graph, right? After removing X. Now what I do is that I look at the component C1 together with the vertex X. So X has neighbors to C1. So I look at all these neighbors. Including, including the component C1, I look at this subgraph. Now, of course, this subgraph is a smaller graph than G, right? So if G was a minimum counterexample, then to three colorability, then this graph, the component C1 plus X, that subgraph is definitely three colorable, right? Similarly, C2 with X is also three colorable because it is smaller than G. Similarly, Ck with X is also three colorable. So therefore, Ci union X is all three colorable strict subgraphs of G, which are all three colorable. Now this tells that the graph G itself is three colorable. Why is that? Can you think about this? Okay. So if each component with X is three colorable, then I claim that the graph itself together with X is also three colorable. Now this is easy to see because if I look at any coloring of C1 with X, X will get some color, let's say red in that, right? Now C2 with X also have a coloring, but X may be given getting a color, let's say blue there. But now it doesn't matter. What I do is that I take the component C2, then I will change the name of the colors. All blue vertices I will call green, and all the green vertices I will call blue. I just rename the colors blue and green, right? Exchange the colors. So that the coloring of C2 with X is still proper, but X will get the color green again. Similarly, I can do it for each of the component. So I will make sure that X gets the same color in all the coloring of the subgraphs. So therefore, altogether, again, it will be a proper coloring because each component gives a proper coloring. With X getting green, I will get a proper coloring of the entire graph. Now, vertex of degree less than or equal to 2 you cannot be part of a minimum counterexample because if I look at G minus X as a subgraph, G minus X can be three colored, means that I can extend the coloring to include x also, because if you look at the vertex x, it has at most 2 neighbors. And since I am using 3 colors, even if x is seeing 2 different colors in the neighborhood, the third color is never going to be used in the neighborhood of x. So therefore, I can give x with that color. So therefore, that also is easy. So therefore, vertices of degree less than or equal to 2 or vertices of which are cut vertices cannot be part of minimum contact sample. So therefore, they are reducible configurations for 3 colorability. Now, we want to prove the theorem. For that, it is sufficient if you show that every planar graph without cycles of length 4 to 11 contains either a cut vertex or a vertex of degree at most 2, right? Because as we just observed, the class of graphs without cycles of length 4 to 11, all the subgraphs also has this property. Okay, if there are no cycles of length 4 to 11 in a graph, if I delete something, you cannot create a cycle of length 4 to 11. Okay, therefore you will see that any subgraph will have this property. Now what we are saying is that every such graph contains either a cut vertex or a vertex of degree less than or equal to 2. Therefore, none of the minimum contact sample to the 3 colorability can be any of these graphs. But if there is a counterexample in this class, I can always talk about the smallest counterexample, right? And therefore, it cannot be there. So that is the idea. So to prove that any such graph contains either a cut vertex or vertex of degree less than or equal to 2, we are going to use the discharging method. So again, we start with the charging phase. So what is our charging phase? We are going to assign a charge d of v minus 6 to each vertex of the graph. So the degree minus 6. This is the one that we did in the first example, right? The trivial example. So the charge of v, phi of v, is dv minus 6. Then we assign a charge twice the length of the phase minus 6 to each phase of the graph. Again, the charge of phase is 2f minus 6. So the total charge is summation over all the vertices, degree minus 6, plus summation over all the phases, 2f minus 6, which is actually equal to minus 12 by Euler identity. Now, why I say equal is that because we assume that there are no cut vertices, one can show that this is actually an equality, right? Every phase is actually incident to exactly 2 phases, and that will tell you that the Euler identity appear as an equality. I mean, in the summation, you will get not Euler identity. The degree sum will appear as an equality. So therefore, you will get the total charge in the graph to be minus 12. And this is true for any planar graph in this class that we are looking at, right? So any such planar graph will have total charge be minus 12. Right? How large the graph doesn't matter. Whatever the size of the graph, the total will be always minus 12. Now, we come up with the discharging rule, right? So the discharging rule says that every phase with length at least 12 sends a charge of plus 3 by 2 to each of its vertices. Now, this might look like a kind of odd idea, right? I mean, how do you come up with the discharging rule? See, to learn the discharging method, the important fact is to see how you come up with the discharging rule. Now, this is not always an easy phase, but here is the idea what we want to do here, right? So the idea of the discharging method, as we mentioned before, is to show that we first start with a charging and take the total charge, right? The total charge, I will show that, is going to be a fixed number, right? Or either negative or positive, right? So here we showed that the total charge is negative 12, which is negative number. Then the idea is that you move around the charges, right? To show that there is some structural properties like the reducible configurations are present. What we are going to show is to move around the charges and say that, okay, after moving around the charges, if the particular property that we want is not there, then the total is going to be different. Now, if I can show that the total is going to be different, then that says that there is something wrong with the assumption, that we assume that there is no reducible configuration present. That was the problem, and therefore we can show that it must be present, right? So it's unavoidable. Now, what we want to show in this case is that since the total charge is negative, I want to somehow show that the total charge is going to be non-negative if there is no cut vertex or vertex of degree less than or equal to 12. So the idea of the charging is to make sure that the total charge will be non-negative if we assume wrongly, right? We assume that there are no cut vertices or vertices of degree less than or equal to 2. So for that purpose, we have to design the discharging rule. So how to move around the charges depends on that. So the ones with the least negative charges should get a lot of positive charge so that it will become non-negative. And the one with with already positive charge does not need to get anything, maybe, right? And others, depending on the cases, you can decide how much charge it should get. So this is how you design the rules. So in this case, we look at this questions and then come up with this following rule: at every phase with length at least 12 sends a charge of plus 3/2 to each of its vertices. Now, let us see what happens, right? So first observation is that if there is a vertex V, which is not a cut vertex, then we observe that it is incident to at least degree many distinct phases, right? All the phases are distinct phases. If a vertex is not a cut vertex, then we say that each of the phases are distinct phases. Now, our claim is that for the class of graphs that we are looking at, every vertex is incident with at least ceiling of degree by 2 distinct phases of length larger than 12, greater than or equal to 12. Okay, so large phases. Okay. So I call a phase large if the length is at least 12. So we are saying that for every vertex, it has at least ceiling of degree by 2 many distinct large phases incident with it. Now, why is this true? This is true because of this property, that if you look at any vertex which is not a cut vertex, it has exactly degree v many phases, and now, right, it has exactly degree v many phases. But now, two adjacent phases of the graph cannot be triangles. Okay? So I claim that two adjacent phases cannot be triangles. Right? This is not possible. Why is that not possible? Can you think of why two adjacent vertices can be 3 cycles? So think for a few minutes before we proceed. So if you have thought about this, you must have observed that if I have two adjacent 3 cycles triangle, then they together form a 4 cycle, right? This 3 cycle plus this 3 cycle, right? This forms a 4 cycle in the graph. But we look at graphs which does not contain any cycles of length 4, 5, 6 or up to 11, right? So since there are no 4 cycles in the graph, right, you cannot have two triangles sharing an edge. But now, since I have degree many distinct phases, only alternate phases can be at most small phases, right? So if I have a small phase, if I have a small phase, then the next immediate phases can be only large, and then the alternate ones can be again small, but then again this must be large, but this also must be large, right? So therefore, at most degree by 2 ceiling, I mean floor many can be small triangles. Therefore, the remaining, which is ceiling of dv by 2, must be of length greater than or equal to 12. And why is that? Because we don't allow cycles of length 4 to 11 in the graph anyway. So if there is no 3 cycle, then the next is going to be large cycles, right? Okay, so that is our observation that if you are looking at graphs in the class pi, then every vertex is incident with at least ceiling of degree v by 2 distinct phases of length at least 12. So this tells you that these phases are going to give you these many phases are going to give you positive charges, right? Plus 3 by 2. Now, again, by our assumption, the graph has no vertex of degree less than or equal to 2. Okay. So the second assumption was that we are looking at graphs and showing that there is no cut vertex or degree less than or equal to 2, right? So by assumption, our graph does not have vertex of degree less than or equal to 2, because if it is there, we are already done. Now, therefore, what happens after the discharging, right? So after the discharging, each vertex gets a charge plus 3 by 2 from each of its degree by 2 ceiling many phases, right? Of length greater than or equal to 12, right? That many phases are incident. So we see that after discharging, every vertex gets this many charges, right? So let us see what this implies. This says that for every phase, right? If you look at the length of the phase can be either 3 or 12, 13, etc., right? If the length of the phase is 3, then its charge is not affected, right? Because the small phases does not give away charges. It does not get any charge, so therefore its initial charge remains. So what is the initial charge of a 3 cycle? Is 2 into 3 minus 6, which is 0. So all the triangles still have charge 0, which is non-negative. Now, if you look at a phase of length greater than or equal to 12, it is 12, not 2, right? So greater than or equal to 12. This vertex, this phase gives away, this phase gives away plus 3 by 2 to each of its vertices, right? So what happens to each of these vertices? It gets plus 3 by 2. But what happens to the phase? Its charge decreases by 3 by 2 into the number of vertices, right? So it is 2 times the length of the phase minus 6 is the initial charge, minus 3 by 2 into cardinality of f, which is the charge it gave away. Now what is this? Which is f by 2 minus 6, right? Length of f by 2 minus 6. But length of f by 2 minus 6 is greater than or equal to 0 if f is greater than or equal to 12, right? Large phases has the enough surplus charges to give away and still be having non-negative charge. So we designed our number 3 by 2 so that this works out also, right? Now, for any vertex V, right? So we saw that every phase after the discharging has non-negative charge, right? Now, what happens to the vertices? So if you look at any vertex, its initial charge was degree minus 6. What happened to it? It got, from all the large phases incident to it, it got charge plus 3 by 2. So what happened to the vertices in the graph? It has degree either 3, 4, 5, 6 larger numbers, right? So if the vertex degree was 3, its initial charge was minus 3. Okay? So initial charge was minus 3. But then what happened to it? It has at least degree by 2 ceiling, which is ceiling of 3 by 2, which is 2. 2 vertices, where it has at least 2 large phases incident to it. And these 2 large phases must have given it plus 3 by 2 charge each. So 2 into 3 by 2, which is plus 3. So the vertex degree 3 gets a charge of 3 from its phases. At least 3, right? So therefore 3 plus minus 3, which is 0. So its charge becomes 0. Right? So we designed our number plus 3 by 2 so that this also happens. Then again, what happened to the vertex of degree 4? Its charge becomes, it was potentially minus 2, but it gets at least 3 again. So therefore it becomes plus 1. Similarly, degree 5, it gets actually 3 times plus 3 by 2. So it is going to become positive again. And degree greater than or equal to 6 is going to be always greater than or equal to 0, because it is not going to lose any charge. It's only going to get positive charges. So therefore, every vertex of the graph after the discharging has positive charge, right? Non-negative charge. Every phase after the discharging has non-negative charge. This says that the total charge is going to be the sum of all the vertex charges plus sum of all the phase charges, which is going to be non-negative. But this is impossible, right? So after the discharging, we see that all the vertices and the phases has non-negative charge, which is impossible. Now, why this impossibility came? Because we assume that there were no vertices of degree less than or equal to 2, right? If there is a vertex of degree 2, by doing this discharging, its charge, which was initially minus 4, need not become positive, right? Similarly, if there was a vertex which is a cut vertex, this could also not become negative, because it might have several phases that we overcounted, because 2 of the phases that we are thinking are different might be the same. So it may not have enough phases to give its positive charge. So the total charge after discharging will be negative, and that happened to be non-negative only because we assumed wrongly that there is no cut vertex or vertices of degree less than or equal to 2. Right? So that is the idea, and this proves that there must be a cut vertex, right, which gives this kind of situations, right, where we don't have a degree by too many large phases, or degree 2 vertices, which also will not become non-negative. So at least one of these must be present in the class, because the total can never be non-negative, right? Because it was minus 12. So this establishes the result, right? Now here is a nice homework question, right? So let G be a planar graph where there are no cycles of length 4 to 10, right? So we started looking at the question 4 to 11. Now we say that, okay, we allow 11 cycles, but there are no cycles of length 4 to 10. Now, can you show that the graph is 3 colorable? I claim that this can be done by slightly modifying the proof that we did. So take it as a challenge and try to do it. It may be a little hard work, but it will be nice. Now, again, I think I mentioned this already, that the conjecture that the planar graph with no 4 cycles of length 4 or 5 is three colorable is a false conjecture, because the conjecture was disproved a couple of years back. But still open question is that if there are no 4, 5, 6 or cycles in the planar graph, can we say the graph is three colorable? So an overview of what we did was that we know the discharging method works as follows. We want to show some property is true for a class of graphs, right? So we have a class of graph phi. We want to show some property P. We try to come up with a set of substructures, right? Like, like the examples we saw, cut vertices, degrees of small degree vertices, or some other things like that. Certain configurations are reducible for this property. So try to come up with such such substructures. For this property, it is reducible, that no minimum counterexample to this particular property can contain this. Now try to show that is it possible to show that one of the structures must be present in the class of graphs that we are looking at, or for what class of graphs we can show something like this. And if you can show that it is unavoidable for that particular class, we know that the property must be true. And to show this, we do the discharging, and the discharging is by giving some initial charges. This initial charging will depend on what we do with the discharging phase. Now the discharging phase depends on what we want to actually show, right? So depending on the type of property that we want to show, we have to design the rules of moving around the charges. And once this trial is there, you can try out whether it works, or if you can slightly modify it, then you can again try to change something like this, or you can change the reducible configuration sets itself maybe slightly, and try again with different discharging rules. So, and at some point it works out, then you have the result, right? So that is the basic idea of discharging method. So try this homework, and with that we can stop this short introduction to discharging method. So I can give you more interesting questions on this, and maybe look at some related topics later.